So we've been talking about work. Now let's spend a few moments talking about heat. Remember, heat is the other way that we can transfer energy between a system and its surroundings across those boundaries that we've defined. This is the form of energy that's transferred due to temperature difference. It is going to be path dependent. We have a sign convention. Everyone uses the same sign convention. Heat into the system is positive. Heat out of the system is negative. You also probably learned in some earlier class, maybe even when you were, young, 10, 11 years old, that there were different ways that heat transfers. And the three modes of heat transfer are conduction, convection, and radiation. Now, I don't want to spend a long time on this, but briefly, conduction occurs primarily in solids. It can also happen in liquids, but this is due to molecule-to-molecule contact. Okay? Convection is due to molecules in motion that bump into each other, contact each other. So this will happen in gases and liquids, but not within solids because they're not in motion. Radiation happens, that's how the sun provides energy to us down here on Earth. Basically, it's electromagnetic energy moving in the space between molecules. So molecules get in the way here. So conduction is happening by molecules touching each other, in contact with one another. Convection is more glancing blows from one molecule to the next. And then radiation is energy moving in the space between molecules. You're going to study a lot more about this in a heat transfer class, so for our purposes, this is way more than we need to know. But there is one very important thing in this section, and that is that we are frequently going to talk about a process being well insulated, or then we will say that Q is equal to 0. And when we do that, the word we use is adiabatic. Now, adiabatic simply does mean that the heat transfer is so limited that it's essentially 0. It's negligible. Nothing truly has no heat transfer. We can't insulate anything that well. But I think most of you, have used a thermos or something like that where well insulated, it didn't seem like it lost a lot of heat. Adiabatic seems like a reasonable assumption. And in industry, we're going to find that there are a lot of cases where that applies. So in order to work a problem, what I really need to do is talk a little bit about some of our properties. And first, I want to talk about internal energy. Now, this is a pretty simple-minded property. We've been talking about it. We've used it. You have used it in other courses. This is the one that I just say this is sort of what you have because you have a temperature. And you can graph this, whether it's pressure versus internal energy, temperature versus internal energy. It's going to be very much like the volume. And the data is in the appendix, and we've been using that data in this course so far. So what I want us to do is use this with our definition of the first law, or the energy balance, to work a basic little problem here. So I want to evaluate the heat transfer needed to evaporate water in a piston and cylinder. So piston cylinder means that the material can expand. Okay, the volume will change, but it will still be trapped inside a closed system. And initially, I've got material at a saturated liquid, pressure given as 1 megapascal. Process is quasi-equilibrium, simply meaning that all of my equations apply. And it ends when the fluid is a saturated vapor, so I'm starting at saturated liquid. This is when we say the quality is 0. And it ends as a saturated vapor when the quality is 1. So how are we going to work this problem? Well, I'm going to need to look up data. So let's go to the appendix. Remember, we always start with, and I didn't mention that this fluid is, oh, there it is. I was going to say it's water. I know I just looked it up. It's water. Okay, so it's water. I want to start at the saturated water table. Whenever I'm looking up data, I always start at the saturated table for that substance. So let's do that. All right, so what they gave us, quality is 0 at the beginning, pressure is 1 megapascal, quality is 1 at the end. I want to find the heat transfer. I am assuming it's constant pressure. Now, why would I assume that? Well, okay, it's trapped. It's in a piston cylinder. The force of the piston shouldn't really change external force. It's just the atmosphere pushing against it. So that pressure shouldn't really change. Also, I'm all inside saturation region, so that's another reason why I might assume this, but it seems very reasonable in a piston cylinder, if they haven't applied any extra force, that it will be constant pressure. They also said nothing about kinetic or potential energy, so I will assume that those are 0. If I write my first law, I get Q equals W plus delta U plus delta KE plus delta PE. These are 0. Okay. And the work said it's quasi-equilibrium. The integral of P dV, well, if I've assumed pressure is constant, then P times delta V. So I need data. All right. Pressure of 1 megapascal, quality of 0. Turns out that it's going to happen at 180 degrees, VF, UF. And I know it's going to end as saturated vapor, VG, UG. Plugging those numbers in, okay. Now, a kilopascal times a cubic meter is a kilojoule, so I converted my pressure from megapascals to kilopascals. Plug those numbers in, I get 2015 kilojoules per kilogram. I assume that running numbers on a calculator you can do at home on your own. Okay, so that was interesting. I've gotten to use my definition of work, and I've used that with the first law, or the energy balance, to solve for the Q. So now let's take this same cylinder. It's got a saturated vapor in there, but I'm going to continue heating it at constant pressure until the temperature is 600 degrees. So it was 180. Now I'm going to take it up to 600. And I want to find out how much more heat transfer is required. Okay. So 1 megapascal, 600 degrees C. This is superheated. This is not one I have to interpolate. Hey, if I make up the problems, I get to do ones that don't require interpolation. The volume is 0.4 meters cubed per kilogram. The internal energy is 3,300 kilojoules per kilogram. The formulas stay the same, right? So here's my delta U. Here's my P delta V for the work. And I get 920 kilojoules per kilogram. Now, one of the things that I think is really important for you to notice is, okay, the first process, there was no change in temperature, but I was heating it from saturated liquid to saturated vapor. It's still saturated, though. It's still in this boiling process. And for that process, the amount of heat transfer required was 2,015 kilojoules per kilogram. And the second one, it was a vapor the entire time. I went from 180 degrees to 600 degrees. That's a huge temperature change. And the Q required for that was only 920 kilojoules per kilogram. It's something that you should just keep in the back of your mind. Heat transfer associated with phase change, which is our latent heat, can be really a surprisingly large number. Okay, and this is sort of the basis behind how things like swamp coolers work for quasi-air conditioning, outdoor areas in deserts. Okay, you've been to amusement parks where they use those misters to do cooling. Same sort of concept. These are taking advantage of the incredibly large latent heat transfer when I have a phase change. Okay, so this concludes our classes for our snow day, February 3rd, and I will see you in class Wednesday morning.